Welcome, everyone. I appreciate all of you joining us today. We're going to be discussing how to architect data storage solutions with CosmosDB. This is going to be a pretty deep conversation and also a bit broad. So we're going to cover a number of topics very quickly and try and give you an exposure to what is CosmosDB and how is it different from some of the other data solutions you might have dealt with in the past. I am Ken Muse. I am the consulting director at Wintellect. For those of you not familiar with Wintellect, we provide consulting, training, and cloud managed services. So we can host websites and environments in Azure for our customers. If you have heard of us, it's probably because we wrote the book on many of the topics that matter to developers and that have mattered to developers over the years. Our team's been instrumental in helping to evolve the landscape of cloud technologies and teach customers how to most effectively use those. So, as I mentioned, in this session, we're going to cover a number of things, starting with some of the basics of CosmosDB. What are the core features and functionality? What are some of the key aspects you need to know if you're going to be creating data models? And along the way, what are those tips and tricks for working with Cosmos? Because this session is going to provide a lot of material in a short time, definitely feel free to reach out to us afterwards if you've got questions or need clarification. We will have a Q&A at the end of this session to give you a chance to get some of those questions answered right after this webinar. So to begin, what is CosmosDB? This is really a very broad description of it, but essentially, CosmosDB is Microsoft's distributed multi-model database service. Now, globally distributed is very easy for us to grasp. That usually means, simply put, that this is available in multiple locations all around the world. That is, I can quickly configure a Cosmos database environment to be available to me almost anywhere in the world, and I can actually link these together so that I can create failover, I can create multiple writable copies and numerous readable copies so I can maximize performance and scale. Currently, there's over 30 regions worldwide supporting it and supporting that multi-master and failover support. And when we say multi-model, what we're really talking about, and I'll come back to it in a moment, is that CosmosDB is designed to support numerous different ways of working with data. And I'll go over a few of those further into this webinar. But essentially, whether you're coming from a SQL background, a MongoDB background, you've worked with Cassandra or simple key value stores, Cosmos is designed to be able to create models that work for you in each of those different types of environments. And it has support for crossing between some of those environments so that you can take advantage of additional functionality, such as perhaps you need to do graph queries on some of your data. Perhaps you need to be able to look at the data through SQL statements. The multi-model approach makes all of that possible. Under the covers, Cosmos is storing the data in a way that gives you high performance, low latency, and the ability for them to provide these abstractions on top of your data, which makes it appear to follow the rules of systems that you may be more used to. So, diving a bit deeper, when we talk about this as a globally distributed system, what we're also talking about is a system that's designed to scale elastically. That is, if I need more power, I can quickly provision that for my instance. Under the covers, this is a combination of CPU, memory, disk allocation, among many other things. And Cosmos refers to all this as a request unit, or RU. And I can choose to have that dedicated, meaning that my particular collection or container I'm working with has all of the performance allocated to it. I can have that same performance allocated across multiple containers. Perhaps they each have different peaks that are complementary. And so it's similar to having multiple databases on one database server. Or perhaps I want to have it with one of the more recent changes, completely serverless, where it scales up and down within a range, completely depending on how much is being used. At the end of the day, RUs are the basis for many of the things we will do in CosmosDB. The more RUs provision, the faster it may be able to respond or analyze the data, and the more dedicated performance we have from the system. Now, as we provision these RUs, there's going to be a number of things that we have to consider, including the fact that more RUs are required for more strongly consistent models. I'll talk about that in a minute. And if you want to use features like multi-write, where I could write to multiple different instances, but all of the data is synchronized, well, then that's going to need additional RUs to deal with the performance of the integration of that data across the different regions. When we want to set the RUs, we can choose to simply provision it, either auto scale on creation, giving it a range, or manual. Now, there's a number of pieces to be aware of as we do that. First of which, request units are the fundamental unit of measurement. They control both your price and your performance. You can scale up and down, but whatever RUs you've provisioned, you are paying for. The more RUs available, the more performance it gives you and the more concurrent load it can tolerate. The RU request, each request for a query to Cosmos will return back to you what was the cost of that. And so it is possible to analyze each query to find out how many request units is it using and optimize it. Now, when we say one RU or one request unit, what we're really saying is that this would be the equivalent of reading a 1 kilobyte JSON document in 1 second. So 1 RU per second, 1 kilobyte of information in 1 second. We can provision this at the database or the container level, which means I can say that everything shares this, or it's specifically narrowed down to just the individual container where I'm going to be storing my data. And this will become clear as we go further in this presentation. The RUs are paid by the hour, so if you're going to use 1 minute at a higher RU, you might as well take advantage of the other 59 that you're paying for. It's worth knowing that the range of those, it's incremented in 100 RU increments. Can go up to 1 million RU, although you can request more through a support ticket. But there's a catch to all of that you need to be aware of if you're developing. You need at least 10 RUs per gigabyte of stored data, and Cosmos will let you know when you need more RUs. And whatever maximum you use, you will not be able to change the value to anything less than 10% of that number. And so if I increment to 5,000 RUs, then the lowest I will ever be able to set my collection to will be 500, or 10% of that 5,000 max I used. If you need to have more variability, then you may need to look at more containers. So what does a request unit mean in terms of when I'm developing? What's the cost of the different actions I might take? Essentially, reads are 1 RU per kilobyte. Writes require about 5. Because a delete is a type of write commit, it also uses 5. Updates are a little bit unique in that they need 10 RUs typically to do a single operation per kilobyte of data. And the reason for this is that you're essentially doing a delete on the old record and a write of a new record. And there's a read operation that occurs in there, but it largely rolls into the costs of the other two. Now, no matter what you do, the lowest amount of performance you can do is 1 RU. And the numbers I'm giving you here can vary based on a number of things, such as item size, property count, indexing, and we'll kind of dive into that as well. So as you increase the number of properties, that is the number of name value pairs or the number of properties if we're talking a JSON document, then it's going to increase the number of RUs we need for each operation, especially reads. Because as we add more properties, there is more information that has to be stored by Cosmos and more properties that need to be indexed. By default, Cosmos indexes everything. And so we may choose to have it not index quite as much just so we can get the additional performance. Now, there is one caveat to that. If you're using the Cassandra APIs, it does not index all attributes by default. It indexes a single attribute, and you can turn on secondary indexing to add one more index. The other models do follow this basic rule. If you write complex queries that need to span partitions, then that is also going to increase the RUs, because the more things Cosmos has to query, the more it has to read, the more RUs it's going to have to use. And when you have unique keys defined, when I do an insert, it's going to need to make sure that that key is globally unique, and so it will need at least one RU value for that, or one RU to execute that for your operation. So writes will take a little bit more of a hit when you're doing a unique key index within your documents. And finally, if you want to use the bounded staleness or strong consistency model, which I will talk about consistency models in a minute, that requires twice as many RUs for every operation. There's a lot of trade-offs in Cosmos, and it gives us the power to choose where we want to make those trade-offs so that we can maximize that cost performance benefit between the different parts of the system. If we're using strong consistency, we're wanting a more traditional database-like level of consistency, where my writes are guaranteed to be committed and everyone sees those writes before I can do my next operation. Well, that does require more effort from Cosmos, and so it needs more RUs to achieve that. Now, when we're trying to get scaling of this system and get the most out of it, minimize RUs, maximize our ability to use Cosmos, everything comes down largely to our choice of how we partition the data. What is our partition key? You get one partition key for any data you're storing in a given container, and that partition key determines exactly how that data will be stored and organized under the covers inside of Cosmos. If your queries are going to be able to do point queries, if I can request things by its specific key, by its identifier, I'm going to get the absolute best performance, because if I can get to the individual object, the identifier, I can jump right to a specific record on a specific system. If I need to go deeper than that, being able to at least stay within a single partition is going to give me the most performance. Now, why is this? Because under the covers, a logical partition is going to be associating all of the data together that shares the same partition key. And it's going to begin assigning that to physical partitions. So a single partition key is guaranteed to be stored on one and only one physical partition. A physical partition has a reserved amount of compute and storage, and so it can quickly scan everything that it holds within that singular partition. Because I'm only having to work with one instance, one indexed server, essentially, I'm able to get responses back very, very rapidly compared to if I have to query all of my estate. So this is one of the single most important things to know about optimizing your work for Cosmos. You're going to want to make sure to consider, what is my partition key? So, like many big data solutions, we'll begin with the end in mind. What are we trying to report on? What kind of things are we most frequently keeping in the where clause for organizing and grouping our data? So if I wanted to be able to find out all of the cats by year, well, I could do that, and I might want to partition by year. And that way I can get back everything grouped by the same year. Now, if I wanted to find everything organized by city, if I was doing my reports based on what's happening in a given city at a given time or between two date ranges, well, in that case, I may want to partition on city. And that would ensure that all of the data related to the same city is stored together. So as I walk through an example, let's say that that's how we're going to do it. We're going to work with a city, and we want all of our data generally to be grouped and reported on by city when we're talking to this particular container. So as I mentioned, partitions are organized by that key. In this case, I've got 3 partitions, each one containing a number of cities. When I want to add something into CosmosDB, it's going to hash my partition key, giving me back a number that I can use to then quickly figure out what is the physical partition holding that information. So let's say that I want to write another record for New York City into this partition. I'm going to be able to take the hash of NYC. It's going to identify the third partition, and the data would go there automatically. That way, all of my New York City data is together. In this case, it's also going to see something else, that partition is nearing being completely full. And so, in order to try and keep the ranges distributed and keep all of the data that's in the same key together, Cosmos is going to have to reorganize. And it will do this for me automatically and without any intervention. And so as that new value comes in of New York City, Cosmos is going to create a new partition. It's going to shuffle the original data to the new partition, and then it's going to write the new incoming data directly to that partition, combining all that data together. And this ensures that if I wanted to make a query on Atlanta, all of those related records are close together, and the only indexes I have to look at will be the ones in the Atlanta partition. As I said, this is a great way to maximize the performance of Cosmos because your RUs are tied to that one instance, and therefore only one server is consuming RUs to read indexes. Now, server's a bit of a simplification, and I'll walk through what really are partitions in a minute. But as a lead into that, it's worth thinking about the fact that when we talk about a partition, the RUs you provision are distributed across those partitions equally. So if I've partitioned 30,000 request units, and I've got 3 physical partitions, each one gets 10,000 RUs. That means that for my queries, I don't truly have 30,000 RUs available to any one partition. I have that available across all of the partitions. And so, depending on your partitioning strategy, this can affect your overall performance. If I need to create an additional partition, as we saw in that last example, then Cosmos is going to provision it and redistribute the RUs automatically. And so now each of those partitions supports 7,500 RUs. This is why it's also very important to consider that partitioning strategy, because how those RUs will be consumed is really all around how you think about your partitioning. Now, a common challenge that comes from this comes from the hot partition or a query fan-out. If either of these situations exist, the performance of Cosmos will suffer. Let me give you some examples. Let's say I've got a number of records that need to be written, and they're all coming in very rapidly, and they're all coming in for New York City. As a result, all of the work is being done in one partition, and the other three are largely sitting idle. We call this a hot partition. Hot partitions will hit your throughput and storage limits very quickly because they're taking on all the load. And so that's the other key concept in thinking about a partition. I don't want everything to hit a single partition based on my key. If you're partitioning by year, for example, then what would happen if 2020 data is coming in? All of my records for 2020 are going to the same one partition. Consequently, one partition is taking all of the hits from writes, and each of the individual partitions, while they may be optimized for the reads, they'll be individually also suffering if they come under a heavy load for write. So we want to be very considerate of which keys are being written to try to distribute them. So we're looking for that trade-off of how do I maximize how many things that are related to each other are located together, and at the same time, how do I minimize the risk that when I write, I end up causing one partition to take the entire load? I'll give you some strategies for that as we continue on. The other big problem we hit is what's called a fan-out query. This is when you end up executing a query where the filtering cannot identify a single partition or a subset of partitions to execute against. As a result, it's going to send the request to every partition, ask every partition to execute the query, and then start returning the results. As a result, it's going to use a lot of RUs because every partition is being hit and every partition is having to execute the query. So if we want to avoid these issues, we need to look at trying to target our operations to single partition keys, or even better, single item keys whenever we do reads. Ideally for writes, we want to scatter them. When we create a query that has a filter, ideally we want it to target a single partition at a time. If it can't do that, then at a minimum, try and make sure that it can use an equality or range to narrow down which partitions it's on. So if I'm doing a partition by year, asking for 2015 to 2016 means that it can ignore all of the other partitions that aren't focused on that year. The absolute worst performance comes from querying without any filters, because these will be executed against every partition, and that is going to require a high number of RUs. Now, when you hit your limits, you are going to see that you get an HTTP status back, a 429 code request rate too large, and you're not going to get any results. Essentially, Cosmos is going to let you know you're being throttled and kick it back to you. If you're using the Azure SDKs, then it's going to begin a retry. This is an exponential retry, so it's going to put some random gaps between the attempts and make them get increasingly longer to give time for the request rate to come back down. Think of it like a big bucket with all of your RUs in it. When the bucket is empty, it gets refilled every second on the second. And so all we've got to do is try and get our query in time for the next bucket of RUs to be available to us. So the SDK will try 9 times, and ultimately, after 30 seconds, it'll give up. It'll realize that it's under too much of a load and stop trying. This is completely configurable in the SDK, and because all of this is REST-based operations, you can handle it even more directly and at a lower level if you need to. But essentially, it's important to remember when you hit your RU limit, your requests for reads or writes will be stopped until more RUs are available to handle the request. So we've covered partitions in a pretty good depth. I think everyone can see that that's a critical part of understanding Cosmos. One of the other big considerations is, what does that multi-model aspect mean? And essentially, each of the models is tuned for specific behaviors, specific ways that you're going to want to use it. As a result, your best practices beyond partitioning, and even in considering partitioning, will vary by the model. So, for example, if you're using Cassandra, I mentioned it does not index every attribute. That means that it's going to have to scan partitions for any attribute not indexed. So you have to consider the indexing processes that Cassandra uses as part of your partitioning strategy. On another extreme, Gremlin, which is a graph API, a graph database, has two basic components, edges and vertices. It's going to locate all of the edges together in the same partition by the partition key. And the source of every vertices is also going to be located in the same place. As a result, certain queries will be substantially more optimized than others when you're talking about a Gremlin database and querying a GraphDB. As a result of this, different models treat the partitions differently and have different behaviors. The different models index differently. In short, the different models work differently. And so no matter which of these models you want to use, you need to consider both the Cosmos behaviors, partitioning and keys, and the behavior of that particular model as part of your design process. This means that for those of you who are coming from a MongoDB background or a Cassandra background, you do need to think about it a bit differently. You have to consider how Cosmos behaves in addition to the behaviors you typically saw with Mongo, for example. Porting something one for one exactly like it is may give you performance challenges depending on how you've been handling your partitions within Mongo, depending on the way you had organized that cluster before you moved to Cosmos. So if you think about these pieces, you're more likely to be more successful. And that means each model is also optimized for some use cases over others. If we're talking Mongo or Cassandra, even Azure Table, those are highly optimized for customers that are moving code that relies on using those existing systems. Similarly with Gremlin, it was really designed to try and, as much as possible, trade off to minimize the impact to your code. If you're doing new projects, if you need to do HTAP or tabular models, if you're trying to get the most out of what Cosmos can do out of the box, then Core should be your default. Go towards the SQL APIs. And if you're trying to do everything else, think about Core as your initial go-to. But I put a big asterisk on that because when we say everything else, certain everything else's really do require you to work with Core. For example, if you want to use the new Synapse Link feature inside of Azure to query your data storage using Spark data frames, one, that is Spark, and two, you're going to be, at least for now, working with the Core APIs. And so it's going to give you that HTAP model, but you really are going to have to develop against core. If you're coming at this from the Cassandra or Mongo standpoint, or trying to use the Kubernetes etcd storage, you should be aware that each protocol has documented limitations. And as you learn those limits, there's not a lot of them to really learn, but they do impact how you interact with the code. For example, joins work within a single document. So if you're coming from the SQL world and used to joins crossing tables, you won't really be able to cross documents and do a join in Cosmos. It is not a traditional database. It is a NoSQL store. If you're coming from Gremlin, then be aware that it's doing a breadth-first traversal instead of depth-first. It asks all of the partitions to analyze the request as opposed to going partition by partition. MongoDB, certain language features are not fully supported, and these are fully documented in the Azure docs. They try to make sure that your impact is as minimal as possible, and they're frequently adding new features to make sure that all of the key language features, operations, functionality that you're used to in Mongo are making their way into these APIs. I definitely encourage you, make sure whichever one you're using, to analyze what are those limitations and just get comfortable with them. As I said, there's not a lot, but they can make a big difference in your success in moving to Cosmos. And finally, when it comes to the models, when in doubt, fall back to using the core APIs or the SQL interface. It has the most features and the most functionality available to it. One of those features that is specific to the core model is triggers. Now, for all of you database folks who are saying, triggers, this I understand. Unfortunately, the way they work in Cosmos is very different from what you're used to. So I want to highlight this. This is not a traditional relational database. Cosmos is not going to behave like a SQL Server or an Oracle. It is NoSQL. But triggers do give us an ability to do things that are more like a relational database. Instead of reacting to every insert, every update, every delete, triggers are specifically invoked by becoming part of the HTTP header for a given operation. So when I write a record, I can also indicate that it needs to trigger or execute a specific trigger. When I use a trigger, it's going to run as a single transaction in Cosmos with full ACID guarantees. This means that it does the logic within the trigger will behave more like a traditional trigger in terms of guaranteeing how those operations will execute. Unfortunately, if you're thinking that this solves all of your ACID guarantee problems with Cosmos, you do need to be aware triggers are always scoped to a single logical partition. It has to always follow that partition key. And so as a result, once again, partition key is everything. You're going to want to make sure that because of that, you consider how you have written the trigger and is it sticking to that single partition? Because it's going to run on what's called a primary replica, and it's going to use strong consistency. This means that it will have potentially slightly higher RUs within that replica, and that the information will be scoped to essentially a single instance within Cosmos and then replicated out to the other instances depending on your consistency model. So to kind of recap this part, if you're trying to get the best performance on Cosmos, you're going to want to optimize for the particular model you've chosen, and you're going to want to make sure to use the right model to support your queries. Now, supporting the right model may mean that you also want to take advantage of that partitioning and the differences between the reads and writes and how that data comes together. And this brings me to another topic around performance. If you want to get the most out of things, you can see that if I'm partitioning for my writes, I may be sacrificing the performance of the reads. If I'm partitioning to optimize my reads, my writes are impacted. The best way to deal with this is going to be to use something called the change feed, which is available at this point to most of the APIs. The change feed essentially allows you to have a reactive programming model that works against changes to a given container. So as data arrives, I can say whenever a new record is created or a record is updated, I want to take some action. And that action could be queuing up requests to go to partitions that are read optimized to make sure that I don't overwhelm those read optimized environments. It could make sure that, or it could enforce triggering other actions further down in the system. It can have an effect across multiple other systems. And natively, this directly integrates with features in Azure such as functions. It's a system that allows you to listen for these insertion and update events, and then react to that incoming request to execute whatever your next step is. In some ways, this is similar to the traditional after triggers of a relational database, but the way it's modeled helps to ensure that you're getting the most performance out of your environment and that at any time you can replay the feed if you need to. For greater control, such as replays, the change feed also gives you access to be able to use a pull-based model instead of a push model. Give me all of the changes from some certain marker. And it's going to give me that access to see how a document changed over time. The one exception to that is really going to be around deletes. So the critical things to know about the change feed are that items are going to be sorted by their modification time and organized by the partition key. That means as you read the partition key, or as you read the change key, you're actually reading things grouped together by time and by logical partition. And so as you read through the records, you're going to be getting some grouping of the information automatically. And while inserts and updates will be tracked, at the moment, deletes don't get tracked. Instead, what will happen is when a delete occurs, you're going to find that the record disappears. There will be no longer an insert or any updates related to that record. It just simply is gone. Now, if you actually care about those deletes, if they're important, then add, for the time being, a soft delete field to your record so that you can flag a record as being deleted. That'll show up as an update. You can then act on that, process the data, and as part of processing that event stream, you might actually mark the record for true deletion after that. This gives you a way to work around a current limitation until delete operations are exposed. This has been a pretty high volume request, and so I would expect it to be fixed in the very near future. You also need to be aware that when we talk about the eventual consistency level in a minute, eventual consistency does mean you may see duplicates. Anytime we're dealing with queues or streams, it's important to consider that duplicate data can possibly come through. The eventual consistency level means that changes may get seen at different moments in time by different CosmosDB instances. And so as I'm reading the change feed, I may see those points in time. And so I may see different points of view on the same data temporarily while the consistency is catching up. Everything will still come back in the same order. And so as a result, sooner or later, all of my data becomes consistent And so the behaviors should become consistent as well, and the final data. If you want to use Azure Functions with this model, be aware that is another feature that is currently really tied to the core SQL APIs. And so functions can natively integrate directly with this. If you're wanting to use the other models, then you may be having to do a little bit of your own integration to interact with Cosmos and pull or push data through the change feed. The change feed itself will exist and will be created. You just don't have that automatic ability to get it through Azure Functions natively. So going just a bit deeper, getting a little lower level in Cosmos, a lot of the performance is tied to the fact that Cosmos indexes everything. It flattens out our keys and stores the values. And as a result, it makes it very easy for it to compress this data, to organize it optimally, and to be able to index, especially if we're using the core API, everything with very low overhead. Now, the types of indexes you choose will impact your performance, and so you can adjust the defaults. And if certain fields are never part of the query, I can eliminate the index and eliminate the associated rights that go with it, potentially saving me RUs. There are a few types of indexes, starting with range. These do your typical range type query operations. They also handle, is it defined? Does it exist? Does a string contain? Am I ordering by? Whenever I create a range query, it's going to be able to answer these kinds of questions. Now, there's a special type of index that isn't created automatically, but we can use. We can let CosmosDB know that a certain field actually represents spatial data, and we can do spatial indexing. Now, these aren't created by default, but if we do create them, then this allows us to do things like indexing distances, or do two locations intersect? Is one within another? And so we can improve performance for those kind of queries. Another type of index we can take advantage of is composite. We've got two or more fields or properties that we really want to tie together data on and be able to pull back data based on that. If I want to do an order by multiple properties, or I want to do a filter with multiple properties, a composite index may be the right way to go because it's going to place those things together in the index. You really want to make sure it's two or more properties, at least one of them has an equality, this equals that, and that in your queries, any range operations are defined last. If you follow those rules, then you'll generally see that the index gets hit and you get better performance. I say general because the order, the sequence and direction really do matter. And so you want to make sure that just like a traditional database, you're thinking about the queries you're creating and making sure that things are in predictable orders. Ascending and descending are automatically indexed for you, so you don't really have to worry as much about that. But the order of the properties and that equality range do very much matter. So be aware that at a high level, all indexes or all fields may be indexed unless you're on Cassandra. This is adjustable at the container level. I can say only index certain fields or use certain types of indexes. Whenever we index, that does come at a cost. It may increase our RUs on writes, but that may decrease our RUs on reads. There's truly only two modes supported at this time. Lazy indexing, where the index gets written after the fact to preserve performance, is no longer available. And so it's either a consistent indexing or it's not indexed. I can specifically, when I'm defining the indexes, include or exclude specific paths. As you may remember from the previous slide, The property names themselves are / delimited, and therefore, because of that, I can write some very specific rules around how I want to do the indexing, using wildcards to ensure that specific parts of the path are indexed or excluded. And that takes us to really the last big part of Cosmos to understand: how we get the most out of the consistency, the reads, and the writes. We always hear that CosmosDB is low latency. Low latency is actually part of the SLA, unlike any other database offering. And it's guaranteed to a certain specific time interval for a read or a write operation. Now, if you're doing strong consistency across multiple regions, and those regions are halfway across the globe, well, speed of light will limit that responsiveness, because we do have to travel to and from those further regions to confirm the writes when we're doing strong consistency. But otherwise, generally speaking, you have a very consistent approach to your latency model. And that latency model is really controlled by what's my consistency. Traditionally, consistency with most systems has always been strong or eventual. Strong consistency is more like our ACID transactions. We're guaranteeing that when I write it, everybody gets that update before the next read. We're guaranteeing that what I write, if I then read back, I will get the same exact data. On the other extreme, we have eventual consistency. I do a write, and I have no guarantee how long it's going to take to be able to read the exact data I just wrote. Read consistency applies to any single read operation within a logical partition. Write operations may have to span some multiple set of partitions. CosmosDB, the team decided early on that these two were not enough. You need a little more control, more granularity, because each of these are very extreme. And so as a result, there is a total of 5 consistency levels you can use, which provide progressively different sets of constraints. And the full set of constraints are well documented. But essentially, what this means is I can choose the consistency level that's right for me and right for what I'm doing, so that I can maximize the behaviors that I need to see. It's interesting to note that Cassandra and MongoDB's native consistency levels are mapped to CosmosDB, although not all of MongoDB's concerns are fully supported today. So for you MongoDB developers, you'll want to review that table in the Azure Docs to see how that may align to what you're doing today in terms of the Mongo consistency models versus Cosmos. When in doubt, generally speaking, you're going to aim for session consistency because it gives you a nice trade-off in how the reads and writes are ordered and the performance of those operations. To understand what's happening under the cover, it's worth knowing that a single physical partition in CosmosDB really can be broken down into a replica set, which is the individual partitions, and a greater set of partitions which may be involved, called the partition set, which extends beyond the overall the current region. And the idea is when I do a write goes to the leader. It's then replicated to the followers. And so our consistency models are really saying, how far does that replication have to go before I can acknowledge it and move on? And so if I just write to the leader and then I'm good to go, it's eventually going to replicate to the followers, then to the forwarder, from the forwarder out to any other replica sets in other regions. Eventual consistency says it'll happen when it happens. Usually it's very low latency, but there's no guarantee on the time. As I move through the other consistency models, I'm starting to say, does one follower need to have fully acknowledged? Do both have to have fully acknowledged? Do I have to start getting acknowledgments from the leaders in the other replica sets so that I know that the other regions are seeing the same data? And so under the covers, all of those settings really come down to physical implementations. And how many of those individual environments have to have acknowledged you before you can move on? Each of those activities requires some additional amount of read units. And so, as I mentioned, our request units may be doubled for reads, and that would occur if we're using bounded staleness or strong consistency, because it's going to want to make absolutely certain that it has achieved consistency in the read. And if it hasn't, it's going to need to get that consistency to respond to you. Similarly, as you do writes, the amount of time you wait for that write to be fully acknowledged and then become available depends on how much of the environment is going to have to acknowledge that write operation. While the impact on your request units is minimal, this may change how long it takes to get the response in order to ensure that consistency level. And so what we're really saying here is that the various consistency levels really control that trade-off between how sure do I need to be that everything is in exactly the same state versus how much do I really just want to confirm that the data has been written to some level of readability. Generally speaking, when in doubt, use session state, and that's going to give you the most averaged out, optimized approach to your model. That doesn't mean use session for everything. Obviously, if you're doing a high write model with low reads, something like eventual consistency may make a lot of sense because I can guarantee that one write has occurred and that the rest of the writes will get there at some point. While if I'm doing something that's more atomic, when it happens and I commit to an order, I've got to decrement some quantity. And I need everyone to see that that quantity is absolutely the same. I can't deal with eventual consistency for some other reason. Well, then I've got options. And so this really covers some of the breadth of the features and functionality and how to take advantage of those when you're modeling and designing data storage solutions in CosmosDB. And so with that, I'm going to go ahead and open it up to any questions that we might have. And that way we can go ahead and get your questions answered. Based on your description, it seems my expectation of using Cosmos to have a globally distributed system with write operations in all regions may not be possible or advisable. It is definitely possible to have it in multiple regions. Advisable is another story because you can see there is a trade-off to that choice. You will be dealing with some overhead for that choice. It seems other regions are intended more for read-only operations. So being able to balance that trade-off between reads and writes is going to make it easier for you to decide where you want to draw those lines. Because if I optimize for having writes available in every region, well, then under certain circumstances, I could see noticeably longer latencies than what I might be expecting. And so you're going to have to trade off the latency, the RU cost, for what you're trying to get out of that. In many cases, a nearby write is often good enough, and a certain level of consistency can help you with that as well. Continue on. I was hoping to use Cosmos to have an app service deployed in multiple regions and take advantage of low latency access locally using Cosmos. You absolutely can use it for that, but you have to realize that this is not your traditional database where I write and everyone sees the updates in real time. And the truth is, your traditional database really hides its own complexity from us, which gives us some of those performance trade-offs. It's showing me a view of now, but I do pay in performance the more I try and tighten that up so I always see the latest piece of information with absolutely no staleness. The more we're able to move to something that's more eventual. And to be clear, we're talking typically on the order of milliseconds for eventual consistency. When we're able to take that eventual consistency or a session consistency, then we can have better performance, lower latency, and even with a traditional database, lower locking, because we're getting the most out of the system in that case. Next question. Is it possible to port an existing C# application that works with SQL Server using EF, Entity Framework Core? Would I need to consider rewriting the data access layer? Or if I modeled the database correctly, can I expect to keep the Entity Framework base code? So I'm going to separate that into a couple of things. First, is it possible? Absolutely. Is it advisable? I would not advise trying to take something and directly port it as is, because you've seen partition key is critical. Understanding how the queries work is critical. EF will help you with making sure queries are consistent. It will help you with abstracting out some of the writing of the queries. But each approach is optimized for that backing data store. And the things I might do to optimize for SQL Server may not be the same as what I'm doing if I'm optimizing for CosmosDB. So while you can do it, unless it's a very trivial application, the differences are enough that you may want to consider the specifics of how the two are being implemented and optimize for both. And so that can mean bringing your query model up another level so that you've got a layer that decides how it's going to target reading from the two if you need to read from both. In truth, the two different systems are each optimized for very specific use cases, one being relational and set operations, the other, and OLTP. The other, Cosmos, is optimized for point querying. It does not optimize for things like give me things grouped by or give me a collection of data based on criteria. Cosmos is optimized for point querying. It's NoSQL. And so while you can use or you could use the same code in both places, the two models are so different, it's not advisable. Next question. One time I created one partition key in a collection and had issues trying to update that value in a document update. Are there considerations to that? If you are updating, you don't want to update the partition key. There are certain values that really are required to stay the same when you're working with partitions. And you can see why. If I tried to update the partition key, I can't actually execute the write necessarily on the partition where I've been directed to because it's optimized for a different partition key. And so, yes, you definitely want to consider that you've got to remain in the same partition. And it's going to be the same if you're trying to deal with those triggers. All of those update or insert operations you're doing will need to stay in the same partition, and all that's related to your partition key. Next question. Can I have more than one partition key? Can I change it later? So because of the fact that a partition key directs where a given set of data will be stored, a collection can have one and only one partition key, but I can have multiple collections. And so if you find yourself needing multiple partition keys, for example, to optimize that separation between reads and writes, take advantage of the change feed so that my write goes into one collection. The change feed then moves that over into the other. By being able to optimize how I do that, I can actually use the two different partition keys effectively. And changing a partition is unfortunately a difficult event because unfortunately that means all of your data is physically located in the same place. And so altering the partition key would mean that all of the data stored in CosmosDB would need to be relocated. And so changing it later really is largely going to be focused on how do you properly rebuild and reload that data model in to support the new partition key. So partition keys are incredibly important for you. Are there examples that show a large variety of data models and scenarios with recommendations on how to handle them? In the Azure Docs, there are a few examples. There's also additional examples that have been posted by the CosmosDB team on their blog and in GitHub repos that the team manages. So I definitely would encourage you to review those because in several of the cases, they'll actually walk you through step by step. What does the data model need to look like? How do you optimize it? And how do you actually use the returned RU value to know when you're getting it right, that it's really optimal for what you're trying to do? And then how do you rebuild it and repartition it or realign that data if you need to deal with issues such as the partition strategy wasn't quite right for the activities I need to do? Next question. Will this webinar be available on demand? Yes, we will make it available. It'll be up over the coming days, and I believe that you'll be getting an email with that link. I'm concerned about having dynamic schema in the database and then performance consistency. Should I still choose CosmosDB? Because it is a NoSQL model, it very much works well with a dynamic schema if you're talking about trying to create this, take a JSON file and have a schema that changes over time. Now, what I would say about that is whenever we're talking about schema change over time, the ID and the partition key are two things that we want to make sure we keep consistent or we consider the downstream impact. And always make sure that with any schema of that type, you've got some field or some mechanism that allows you to distinguish different versions of the schema from each other. Otherwise, what will happen is it's going to become very, very difficult to optimize the data you're storing or to be able to narrowly constrain the behaviors or the operations to specific types or sets of data. If you're going to take a dynamic schema where you don't know how it's going to change, no one's managing it, no one's planning for it, CosmosDB can do that, but at some point you could have performance issues because the indexing will continue to grow as the properties get added and changed. And you're going to see challenges as you try and later use that data. What if a column's gone? What if last week it was a string and this week it's a date? What if next week it's a numerical value instead? So just because something is NoSQL does not mean we completely ignore or abandon how we think about schema and schema change over time. Any more than when we say serverless, we mean that you no longer have to consider how does your code behave on the running server environment. Next question. Does CosmosDB support subscribing to the documents changed directly from the front end? Or am I really needing to think about Azure Functions and possibly SignalR? It is a REST API. And so consequently, you do have the ability to interact with it through those RESTful endpoints. That said, I would generally recommend, whenever possible, protecting your systems from direct data access. In the same way, I wouldn't necessarily connect a database server directly to the web UI, even if I could, because there's too many potential downstream impacts to that. You can definitely do things like that, but again, is it advisable? Is it optimal? Especially given that a minor change to the JavaScript could have a very big change in the performance characteristics of how we query that data. And so a good separation of concerns here is definitely recommended. For a greenfield project, do you recommend Google's Firestore over CosmosDB? I don't go as deep into Google's Firestore. That's unfortunately not an area I've spent as much time. But I will say that, especially if you're doing an Azure-focused application or trying to make the most of data and the data platform services in Azure, it is definitely a recommended practice to look at Cosmos and consider whether it's a fit. You're doing key value storage, and so there's a number of the options within the models that can work for you, and where you've got some opportunities to optimize the storage. In some cases, depending on what you're doing, there are other services in Azure that might also optimize for that, such as the table APIs, or even I've seen cases where blob storage was an appropriate key value store because of what was being done. So I would definitely review it against your technical requirements and see how it aligns. And our final two questions. First, is it a good practice to create separate collections for data? For example, header information with a few fields, detail information for the whole model in a record, in order to save RUs. Really, that depends on the data. If, for example, I'm needing to constantly get back some amount of aggregated data, statistics, how many people liked a comment, having that in a separate collection allows me to optimize for the queries that are going to be retrieving that data and to get closer to a point operation. In a similar vein, if I'm reading just some light details about it, again, I might be able to optimize that down to something where it's a kilobyte or less of data, and now I've got a 1 RU read to be able to pull that information back. The more I can do that, the more optimal it'll be. There are times where it is, in fact, advisable to separate the two, because the data you're going to bring back, you may not bring back all the time, or it may be data that requires drilling deeper into the environment where more optimized queries might be a better fit. And so again, it's something where knowing what we now know about partitions and partition keys, you can start to look at that. I'm confused between partition key and index. Can you help me with an example? So as we were looking at that earlier, let me bring it up on the screen here. Partition key. It is a field such as we picked, in this case, let me go back just a touch further. We decided we wanted to partition on New York City. That is, we wanted to physically group data together based on the city. And so as cities come in, they get physically located in the same specific replica set. They are on the same partition. And so Cosmos makes sure that physically they're co-located. When we talk about an index, what we're really saying is, how do we handle all these other fields? Where I said, give me everything where the years between 2015 and 2019. An index will find these other parts within that. And so if I say where city equals New York City and year between 2015 and 2018, Cosmos is going to jump directly to one partition. And then within that, it's going to use the index to find New York City and everything that's within that range, 2015 to 2018. And so indexes help us with those lookups. If I was to say, give me everything between 2015 and 2019 and not specify the city, well, that's when I get to those fan out queries, where it's going to send a request to every server and say, hey, do you have anything that matches that data? And it's going to look at the index against year on each of the boxes, because it can't ask about a single partition, a single environment. Hopefully that helps clarify partition key, which puts us in a singular location, versus index, which allows us to find data within each of these partitions. Should I still consider the classic table storage model to save money? You absolutely can, but be aware that there's really no further investment in the table storage APIs because we frequently found the need for things like secondary indexes, having some control over when schema models change, being able to do range queries. We've quickly found that table became very complicated and very painful. If you've ever tried to do a delete from a table, you may have also seen the same thing, that it can become a bit more difficult to deal with some of those operations, especially since you can only get to it point by point generally. And so, can you consider it? Absolutely. Is it cost savings? Generally speaking, yes. Depends on how much data you're storing and what you're doing with it. And are you willing to accept the performance trade-offs? If you're looking for the additional features, things like being able to use triggers, being able to optimize by the various indexes, being able to use change feeds so that you can have a reactive model that when some record changes, other things happen. In all of those cases, CosmosDB will be a better fit and provide you a cleaner path forward since it's continuously getting new features. So with that, we've gone 15 minutes over. I appreciate everyone who stuck around for the Q&A and everyone who has participated in today's discussion. If you have any questions, as always, feel free to reach out to us. You can find me on Twitter and LinkedIn. And of course, you can reach out to Wenelec directly. And in the coming days, you'll be receiving an email with more information following up on this particular webinar. Thanks again, and we look forward to seeing all of you again soon.